Ну ладно, давайте начнем. Первый доклад у нас представит Сергей Самсонов про снижение дисперсии в алгоритмах MCMC и reinforcement learning. Сережа.
Да, только сейчас, одну секунду. Вы видите сейчас первый слайд? Или...
Мы видим заглавный слайд.
Да.
То, что я его сейчас переключаю, видно, да?
Не видно.
Нет, кажется, Ctrl-F не нажат. Ну, то есть, в смысле, мы видим открытый акробат или что это?
Все, я понял. Сейчас, давайте лучше просто весь экран расширим.
Так.
Так лучше?
Да, так лучше. Ну, да, тут переключается.
Здравствуйте. Я сегодня расскажу недавние результаты нашей группы по снижению дисперсии в методах MCMC и обучении с подкреплением. Меня зовут Сергей Самсонов, я аспирант факультета математики Высшей школы экономики, и я работаю в HDI Lab под руководством Алексея Наумова. Собственно, результаты, о которых я сегодня буду говорить, это, более-менее это результаты, полученные, значит, в 3 статьях вместе с Денисом Беломестным, с Леонидом Осипой, Эриком Мулине и Алексеем Наумовым. Давайте начнем. Наша задача, собственно, стандартная постановка для методов Монте-Карло и MCMC. Мы хотим оценить интеграл от какой-то функции f, точнее, от ожидания некоторой функции f по распределению π. Это интеграл по некоторому пространству x. Можно считать, что это пространство RD, где размерность d, вообще говоря, большая. Поэтому никакой надежды на то, чтобы считать этот интеграл детерминированными методами, у нас нет. И что предлагают нам численные методы стохастики? Самое стандартное решение – это использовать метод Монте-Карло. Если мы можем генерировать независимые одинаково распределенные величины с распределением π, то естественное желание – это нагенерировать такую последовательность величин xk и просто оценить средние функции f с помощью такого выборочного среднего. В этом случае мы можем, в силу центральной предельной теоремы, у нас есть асимптотическая нормальность таких оценок. В силу усиленного закона больших чисел мы можем гарантировать сходимость p от f к p от f почти наверное. Но основной минус, с которым мы позже обсудим, как бороться, он заключается в том, что, вообще говоря, предположение о том, что мы можем генерировать независимые одинаково распределенные случайные величины из π, оно очень часто нарушается. Особенно в тех случаях, когда распределение π нам известно не полностью, например, мы знаем его только с точностью до константы пропорциональности, или в тех случаях, когда размерность d у нас очень большая. И тем не менее, на примере методов Монте-Карло можно обсудить основную идею некоторых подходов к снижению дисперсии. Давайте подумаем, какие вообще у нас есть варианты для того, чтобы снизить дисперсию в Монте-Карло оценках. Понятно, что у нас случайные величины независимые, поэтому дисперсия нашей оценки p от f – это просто дисперсия f по мере π делить на m. Да? Поэтому самый простой метод снижения дисперсии – это просто увеличивать число наблюдений, по которым мы проводим оценку, но это, конечно, не всегда возможно. Простой и популярный способ, описанный в литературе уже несколько десятков лет назад, это так называемые контрольные переменные. В чем заключается идея использования контрольных переменных в методе Монте-Карло? Можно заметить, что если мы из функции f вычтем какую-нибудь функцию g с нулевым средним по мере π, то, конечно, среднее у нас не изменится. Если мы теперь можем подобрать эту функцию g таким образом, что дисперсия f минус g у нас меньше, чем дисперсия f, то в этом случае, скорее всего, эргодические средние функции f минус g – это гораздо лучшая оценка для p от f, в смысле дисперсии, чем просто эргодические средние функции f. Этот подход, в частности, был теоретически исследован в недавней статье Дениса Беломестного, Никиты Животовского, нашего следующего сегодняшнего докладчика, и Леонида Осипова. Значит, в предположении, что у нас есть некоторый класс G контрольных переменных с нулевым средним, предлагается находить оптимальную контрольную переменную как минимизатор оценки выборочной дисперсии функции f минус g. Вот. Оценки такого типа для методов Монте-Карло были известны и раньше. В частности, вместо выборочной дисперсии здесь можно исследовать функционалы типа функции потерь типа least squares, но, правда, уже с худшими теоретическими гарантиями. И возникает вопрос, как строить как, собственно, строить функции g, которые обладают нулевым средним по мере π. Популярный популярный класс таких переменных задается тождеством Стейна. Это так называемые стейновские контрольные переменные. Значит, если есть достаточно гладкая функция φ, то любая функция gφ вида градиент φ на градиент логарифма π плюс лапласиан φ обладает нулевым средним относительно меры π. Это следует более-менее из формулы интегрирования по частям в многомерном случае. И в качестве класса, из которого мы выбираем функции φ, можно выбирать различные классы гладких функций. Можно выбирать, например, нейронные сетки. Можно брать что-то более простое, параметрическое, например, полиномы или какие-то RBF-функции, что-то более классическое. И, в общем, какие-то линейные классы. Вот. Основной недостаток этого метода заключается в том, что мы предполагаем, что нам известен градиент логарифма π. То есть, конечно, если мы не знаем ничего про стационарное распределение, например, мы вообще не знаем выражения в аналитическом виде для того распределения, по которому мы хотим посчитать интеграл, то, конечно, очень сложно применить. По всей видимости, сложно строить контрольные переменные с нулевым средним относительно данной меры. Возникает вопрос, как теперь действовать в том случае, когда мы не можем генерировать независимые одинаково распределенные случайные величины с распределением π. В этом случае популярное решение – это использовать методы MCMC. Мы запускаем некоторую марковскую цепь с правильным стационарным распределением. Значит, оно должно быть либо π, либо должно быть достаточно близко к π. В этом случае, если цепь эргодична, и мы подождали достаточно долгое время, выбросив там первые n сэмплов, то мы можем рассчитывать на то, что распределение нашей цепи уже достаточно близко сошлось к стационарному. В этом случае мы можем оценивать средние нашей функции f с помощью просто эргодических средних, с учетом того, что мы отбросили первый участок траектории в качестве просто Бернина. Но, разумеется, в случае с алгоритмами MCMC дисперсия, вообще говоря, у нас становится больше, потому что у нас появляется зависимость между нашими наблюдениями x-ката. И возникает вопрос, как адаптировать механизм контрольных переменных, который мы до этого описывали в случае методов Монте-Карло, для методов MCMC. В качестве примера популярных MCMC-алгоритмов можно отметить семейство методов, основанных на дискретизации уравнения Ланжевена. Значит, вот здесь и если мы просто возьмем уравнение Ланжевена, возьмем его дискретизацию, полученную методом Эйлера, мы получим так называемый unadjusted Langevin алгоритм для оценки, для сэмплирования из распределения близкого к инвариантному распределению диффузии. Либо мы можем добавить поправку Метрополис-Хастингса, и в этом случае мы получим так называемую малу Метрополис-Adjusted Langevin алгоритм. Вот. Но также отмечу, что в принципе, особенно в байесовской постановке, считать здесь градиент логарифма π может быть очень дорого, потому что он может включать в себя проход по всей выборке обучающей. Поэтому, ну, возможно, в алгоритмах сэмплирования использовать оценку градиента, что ведет к алгоритмам типа SGLD, это динамика Ланжевена со стохастическим градиентом, и ее различным вариантам со сниженной дисперсией, когда вместо градиента Nabla-U используются различные его несмещенные оценки. Давайте теперь запишем выражение для дисперсии эргодического среднего, которую мы получаем в алгоритме MCMC. Ну, предположим для простоты, что мы начали со стационарного распределения π. Ну, в этом случае, конечно, у нас дисперсия, это будет просто дисперсия функции f по мере π делить на n, значит, плюс некоторая взвешенная сумма автоковариаций большего порядка. Ну, конечно, это будет не просто дисперсия функции f по стационарному распределению π. А это значит, что если мы хотим правильно строить контрольные переменные для методов MCMC, мы должны минимизировать не просто оценку выборочной дисперсии по распределению π, а мы должны минимизировать нечто более сложное. Вот. И это и есть, в общем-то, основная идея двух статей, на которые я чуть позже приведу ссылки. Мы знаем, что для марковских цепей, ну, при условии, что у нас выполнены некоторые технические условия, ну, например, у нас есть неприводимость, апериодичность и существует решение уравнения Пуассона, для марковских цепей выполнена центральная предельная теорема. То есть мы знаем, что эргодические средние с правильной нормировкой, они сходятся по распределению к нормальной случайной величине, дисперсия которой – это так называемая асимптотическая дисперсия, которую можно представить как сумму автоковариаций цепи нужного порядка. Это значит, что асимптотический доверительный интервал для P от F в случае оценок MCMC, он имеет длину, вообще говоря, пропорциональную корню из асимптотической дисперсии. А это значит, что при применении контрольных переменных в методах MCMC, ну, вообще говоря, мы должны минимизировать именно некоторую оценку асимптотической дисперсии. Вот. Ну, такие оценки существуют. В частности, здесь на слайде приведена так называемая спектральная оценка, которая основана на взвешенных эмпирических автоковариациях. Ну, таким образом, наш алгоритм снижения дисперсии с использованием контрольных переменных для MCMC, он заключается в следующем. Мы оцениваем асимптотическую дисперсию, соответствующую функции f минус g, через ее спектральную оценку, и минимизируем эту спектральную оценку по некоторому классу функций с нулевым средним относительно меры π. Ну, например, по классу, построенному с помощью контрольных переменных типа Стейна. Ну, и мы можем доказать некоторые теоретические гарантии на так называемый excess риск оценки, полученной таким образом. В частности, мы можем показать, что избыточный риск оценки, полученной минимизацией спектральной оценки асимптотической дисперсии, он имеет порядок единицы на корень из n. Ну, при определенных предположениях на марковское ядро, отвечающее нашему алгоритму, и на класс контрольных переменных, по которому мы ввели минимизацию. Вот. Ну, как это работает на практике? Я приведу только очень игрушечный пример. Это стандартный бенчмарк для алгоритмов MCMC. Это так называемое распределение банана shape. Значит, линии уровня этого распределения при различных параметрах BM, они похожи на банан, если вы возьмете проекцию на первые две компоненты. И как следствие, особенно в областях, которые отвечают краям банана, у нас наблюдается очень большая кривизна линии уровня плотности, а это значит, что мы должны выбирать, ну, например, при сэмплировании с помощью динамики Лонжерина мы должны выбирать очень маленький шаг гамма, что приводит к сильно коррелированным наблюдениям, и поэтому нам интересен variance reduction в данном примере. Вот для функционала типа сумма компонент я хочу вам показать оценки, которые получаются с помощью различных обычных алгоритмов MCMC. Значит, это Юла, Мала и Random Walk Metropolis. Это бокс-плоты, которые нарисованы слева на каждом из трех графиков. Значит, здесь я просто запустил 100 траекторий, 100 независимых траекторий там, фиксированной длины, алгоритма без всяких улучшений. Значит, на центральном бокс-плоте я запустил те же самые 100 траекторий, но при этом с фиксированным классом контрольных переменных мы попробовали применить минимизацию эмпирической дисперсии из независимого случая. Ну а на крайне правом графике в каждом случае те же самые 100 траекторий, только здесь контрольная переменная уже строится минимизацией спектральной оценки асимптотической дисперсии. Вот. Ну, как видно, дисперсия наших оценок действительно значительно уменьшилась. Вот. Ну, больше примеров можно найти в нашей статье в Statistics and Computing и в недавней статье, которая находится на ревизии в SAM Journal of Uncertainty Quantification. Но в чем заключается главный минус этого подхода? Значит, для того, чтобы мы действительно могли снизить дисперсию, значит, нам нужно знать распределение π. К сожалению, на практике это часто не выполняется. Но в частности, это не выполняется в многих задачах обучения с подкреплением. Вот. В алгоритмах семейства Policy Gradient мы были бы заинтересованы в том, чтобы снизить дисперсию оценок нашего градиента, но, к сожалению, стационарного распределения π мы в этом случае не знаем. Но зато мы часто знаем, что наш марковский процесс имеет вид некоторой итерационной последовательности. Ну, то есть каждое следующее наблюдение – это есть некоторая функция от предыдущего…
1-2 минуты.
Да, я скоро закончу. От предыдущего наблюдения и некоторого независимого шума, который мы добавляем на каждом новом шаге. Ну, это типичная задача, это типичная постановка, которая возникает во многих задачах классического контроля. В частности, в так называемой задаче Mountain Car. Вот. Здесь я думаю, что я это пропущу. Просто скажу основную идею построения контрольных переменных в этом случае. Мы можем заметить, что у нас есть… В этом случае для того, чтобы строить контрольную переменную, мы должны что-то знать про нашу случайность кси. Значит, в данном случае мы предполагаем, что мы знаем полную ортонормальную систему относительно распределения по кси. Если мы знаем такую систему фикате, ну, например, для нормальных случайных величин мы можем взять просто полиномы Эрмита, например, то мы можем заметить, что значит, каждую функцию f от x ката мы можем разложить в некоторый ряд, ну, вообще говоря, в ряд Фурье по полиномам фиката от кси. И при этом мы можем заметить, что функция, стоящая справа, значит, даже если мы обрежем это разложение на каком-то конечном шаге, в какой-то момент времени k большое, у суммы справа мат ожидания все еще останется нулевым. Поэтому таким образом мы можем строить функции, которые приближают каким-то образом f от x минус ее мат ожидания, и при этом обладают нулевым мат ожиданием. Вот. Ну, в общем случае это выглядит, может быть, несколько громоздко, но мы можем записать следующее разложение, которое там выполнено в L2. Ну, время уже поджимает, поэтому я, может быть, просто покажу...
Лучше результат финальный.
Я просто покажу в качестве финального результата, каким образом мы это все применяем к алгоритму reinforce. Значит, идея в том, что в алгоритме reinforce мы применяем наше мартингальное разложение для кумулятивной награды ЖКТ, которая у нас представима как сумма будущих наград на каждом шаге К, ну, без дисконтирования. В этом случае, ну, это некоторый аддитивный функционал. Значит, каждая награда РКТ – это функция текущих состояний марковской цепи, поэтому мы можем разложить ее по ортогональной системе, порожденной шумом, который мы использовали в нашей политике, и использовать это для снижения дисперсии в нашем реинфорсе. Ну, вот здесь приведены несколько кривых обучения. Для алгоритма reinforce бесконтрольной переменной, он оранжевый, и для алгоритма reinforce с нашей мартингальной контрольной переменной. Ну, как видно, обучение стало гораздо более устойчивым.
Так, серьезно, спасибо.
Спасибо. Ну, здесь в конце несколько ссылок.
Quentin, do you have a question?
No questions.
Okay. We have Максим Каледин. Максим Каледин, есть вопрос? Максим, нет вопросов. Ну ладно, спасибо.
Спасибо.
Спасибо, да. Тогда мы переходим к Никите. Никита, привет.
Всем привет.
Ты в солнечном Цюрихе?
Ну, в таком солнечном, в плюс 3 или плюс 4.
Почти
Тоже
как в
достаточно
Москве.
холодно.
Почти как в Москве. Так, у нас... Никита, а ты на русском будешь, на английском?
Я могу на любом. Мне кажется, что здесь Кентан. Кентан, would you like me to give a talk in English?
As you want, I don't mind.
Okay, so I'll try to give it in English.
Okay, no problem. So, Nikita, so then I would like to introduce Nikita Животовский from Google Zurich on the power of abstention in statistical and online learning. So, Nikita, please.
Yeah, so thank you very much. This talk is based on two papers. One is with Olivier Bousquet and the second is with Gerginoy, but I'll try to give you a short overview of both of them. So, like, I think many of you are like familiar with basic statistical learning results, but let me recall. So I'll focus on the most simple, most basic problem. So assume that I'm observing an IID sample, xi, yi of n observations. Like xi's are my instances and yi's are the labels, like two classes. Either it's 0 or 1. And I'm given a finite number of functions mapping the instances to 0 or 1. And the usual aim is to, like many people in statistical learning consider the most basic question is like what was told us in the previous talk, the so-called excess risk, like how well I perform compared to the best function in the class, or in the best function in a certain family of functions. And here, the most basic result, which follows from like union bound and Hebding inequality, so it's just an exercise, even not a theorem, known from 60s, is that with high probability over the realizations of the random sample, like with probability 1 minus delta, the probability of error of like the probability of the classifier f hat being wrong and a new pair x y where xy is sampled from the same distribution as our initial sample, and f hat is a minimizer of empirical risk. So like f hat minimizes the sum of wrong predictions over the entire sample. Then this difference is essentially scaling as square root of the logarithm of the number of functions over the square root of the sample size. And yeah, so this is more or less the end of the story for finite families, because you cannot go below 1 over square root of n. So this is something quite fundamental, which follows from like more or less central limit theorem. Even for like two, you may give an example of just 2 functions, the family f consisting of just say all ones and all zeros, and construct such a distribution of the pairs x, y's, so that this difference cannot converge to 0 faster than 1 over square root of n. So this is seemingly the end of the story, and some famous Germans and Russians tried to eliminate this problem back in late 90s and early 2000s. They introduced the following assumption, which is called Mamen-Tsibako. But before presenting it, I need to introduce the bias optimal predictor. So the bias optimal predictor, it's FB star. It's just the indicator of whether y given x is above 1/2 or below 1/2. So in some sense, if given any observation for the true distribution, you know that your expected label is 0.75, which means that the best functional prediction will be to say 1, and vice versa. So you may prove that among all functions, all measurable things, so this binary predictor has the smallest possible risk. But the problem is that, unfortunately, we don't know the distribution. So that's the key of statistics and statistical machine learning. So we use a finite sample to approximate like the true ground truth. So in this case, we're trying to estimate this bias optimal predictor. And what they showed back in the late 90s, that the regularity of this conditional distribution around 1/2 plays a crucial role. So in some sense, like if you know that expected y given x is really 1/2, which means that you have a crazy amount of noise. So you have like a kind of a random coin flipped to predict or like to produce any label. And that's why they introduced like a series of assumptions which are somehow managing to remove these problems. So their first assumption, which is quite strong and is almost never satisfied in practice, is that they assume that the functional class f contains the bias optimal predictor. So like among all possible functions, the best possible function is in your class. And the second assumption is slightly more natural, and it says something like the probability of this y given x, and remember that 1/2 is a problematic region when we just like toss a random coin, that the probability of this expected y given x is very close to 1/2, so it's almost 0, which is bad, and the probability that it's smaller than t is relatively small. So if I have a t equals to 0.01, then this probability will be very small. So I control the amount of mass of x's where the conditional y is approaching 1/2. So this is a very simple assumption, and with some relatively simple but interesting proof, one may easily show that under these assumptions, you immediately speed up the convergence of empirical risk minimizers. So instead of 1 over square root of n convergence on the previous slide, you suddenly have something like 1 over n to the power of 2 minus alpha, and alpha runs between 0 and 1. So you have a full interpolation between 1 over square root of n and 1 over n. So this is like the folklore. But of course, satisfying this is crazy. You will never certify this, especially the first one. So I can assume that there are some like real-world problems which have almost no labeling noise, but the fact that your ground truth function is in the class, it's quite restricted. So our approach is like, is about forgetting any of these nice assumptions because we cannot control them, and better to give the learner or the statistician some extra powers. So this is like, it's just an orthogonal direction which will hopefully lead to similar results. So our question is it possible to replace 1 over n, 1 over square root of n by 1 over n by slightly changing the loss? Unfortunately, there is such a change that we found, and this is the so-called reject option model. So I'm considering a function f now, which is, or classifier f, which is 3-valued. In some sense, it has 0, 1, or star, which is I don't know. So like instead of just predicting with a true label, you have an option to abstain. But of course, with such an option, if you pay nothing for abstaining, like I'm just saying, I don't know, I don't know, I don't know, all the time, then then there should be some price for it. And once again, many years ago, around 50 years ago, there was an influential paper by Chow who introduced the following simple and quite natural risk, so which is defined as RCF. In some sense, I'm having the standard loss, the standard risk of the binary classification when I output 0 or 1. So this is the first part. It has no differences with the binary loss, binary risk. But then if I output star, I pay the price of C. And C, like, it's a fixed price in some sense, and it's assumed to be less or equal than 1/2. Why is it less or equal than 1/2? The idea is that if I just randomly predict the label with star, just toss a random, toss a fair coin each time, and I have on average the loss 1/2. So in some sense, nothing above 1/2 is interesting. But if I have something like C equals to 0.49, then in some sense on stars, I'm beating the random prediction. So that's my setup. And of course, this model was studied by famous guys. So there's a paper by Herbij Wegkamp, Peter Bartlett, and Martin Wegkamp. But unfortunately, in their papers, nothing unexpected happened. So what they did, they considered this RC loss, this Chow's risk, and they were competing with the classes of functions f, which are always 0, also 0, 1 star valued. And this is extremely, for me, it's a bit boring because it's like a standard loss. So there is nothing magical, and you have the same 1 over square root of n convergence. So you just replace the binary loss by a new loss, which is slightly different, but nothing unexpected. We found like a slightly different point of view. We see this like abstention option as like an option available only to us. So that's how we are trying to be as good as possible as the best function in the class. But we don't assume that functions in the class have an option to abstain. So that's very important. This is closer to the so-called aggregation theory. Use the curvature of your loss, leave the class, do whatever you want, but be as good as possible as like a finite collection of functions. And for this difference, so that's the difference I'm considering. I'm trying to construct f, like it should be maybe f hat here, not f, but the idea, I want to make this like predict the loss, the abstention loss, minus the loss of the best in the class, as small as possible with high probability. But seemingly, if I have such a formulation, I'm doomed unless C is very, very small. So if C is like the price for abstention is converging to 0 with n, or if it's 0, of course, this is a simple problem, and I just abstain almost all the time. What is surprising that for our result and for our techniques, a very marginal abstention cost is needed. Like you may think of C being like 0.499 in theory. So which means that I know when I abstain, I'm better than predicting at random, but only very marginally. So there is almost no improvement in some sense. And what we proved actually is that this abstention has a very it's quite strong, even for not only for finite classes, but for BC classes and so on, for some extensions. So So here is the theorem stated a bit informally. Like I fix the price of abstention. It's between 0 and 1/2. We know that it's not reasonable to go above 1/2 because clearly coin flip is having it 1/2 for free. So there is no extra information involved. And we prove that there is a certain classifier, which is defined by hat of C, taking its values, which is 0, 1 star valued. And with high probability, these RC excess risk, like the Chow's risk of this classifier, minus the risk of the best, scales as 1/n. And of course, I have to pay for like C being too close to 1/2, but then this is like 1 minus 2C, which says that if, for example, C is 0.49, then I pay something like constant 50 here, but it's a constant, so it doesn't affect the convergence rates. And fortunately, so you may complain that, okay, I'm comparing slightly different risks and I'm outputting something outside of the class, so it's a bit of cheating. But fortunately, this result contains the old result as a particular case. So why? Because we prove also that if I replace the stars everywhere by just random predictions, which I just flip a coin each time and predict with one of its sides, then no matter what like the value of C is, I always recover the standard optimal bound for empirical risk minimizing. And moreover, the result is completely adaptive to Tsubakov's assumption. So if suddenly I can never verify that Tsubakov's assumption is satisfied in the real world, but this result doesn't care. It's automatically, in some sense, capturing this phenomena if it happened to happen. So we're proving that if I replace all the stars by 1/2 all the time, then the value will be as good as the performance of standard empirical minimizer in the standard context. Okay, so I think I have around 5 more minutes, or maybe even 10, and I'll give you a short explanation of how the algorithm works. So I have a nice picture, and then I will be jumping between the picture and the algorithm because it's easier to understand. Like first, I'm finding the binary ERM, like the standard empirical risk minimizer. If there are many, I choose any of them in the class F. So this is on the picture. This is this dot with a hole inside. Then I find a certain set, which is called F hat, which is called a set of almost empirical minimizers. So I don't define it here, but these are like the functions which are almost as good as the ERM, but like not actually the best performance. So in the picture, you see it's here. It's a subclass of F. And of course, ERM is inside this class. Sorry. Then, based on this stuff, based on this set of empirical, almost empirical minimizers, I define the set of G hat of 0, 1 star valued functions, which are indexed by the functions in the set of almost minimizers, which are defined as follows: like any function Gx is equal to fx if I think it should be like, okay, it's the function, but this is f is indexing, like it's equal to the indexing function if fx is equal to the value of empirical risk minimizer at this point, and otherwise it's a star. So just to understand it better, I'll better show the picture. So this is black points, black functions are the functions inside the set of almost minimizers, and I create the line between G hat and F, and I consider the midpoint, the F plus G hat over half. So this is like 0, 1, 1/2 valued function, which says 1/2 whenever these two functions disagree. And then I just replace these 1/2s by stars. So 1/2 and star for me, it's the same. And sorry again. And then I output the function or return the classifier which minimizes the empirical RC loss, so the empirical Chow's loss among this new 0-1 star value class over the same sample. Yeah, so this is how we construct it, and fortunately it works like a charm and includes the whole analysis and outperforms it significantly. Now I'll give a very short, I think I have 3 minutes or so, yeah. I'll give a very short explanation on how it works in the online setup, and somehow magically it also works with a different algorithm in the online learning setup without any assumptions like IID or it's a completely adversarial setup. Let me give a short explanation of the protocol. So there are capital T rounds, and at each time I repeat the following. I observe 0-1 valued predictions of n experts. Like it's even like you may think of them for a second as like n functions. And based on these observations, I always predict round by round. I predict 0, 1, or star. But then the environment reveals me the true label. So the environment, once again, cannot say star. And even if I put star, so that's our restriction, our environment still shows me it's 0 or 1 answer. So this is like the game where I have an advantage of making the star prediction, and the environment, or in the previous setup, the like true distribution or the functions in the class, they have no such an option. And then I suffer the loss, which is the binary loss if I predicted 0, 1, the same setup, yeah. And I suffer C, which we assume to be smaller or equal than 1/2 if I predict star. And the idea in this online setup is to minimize the regret. So there is like an internal randomization of the algorithm. So we show that you actually need to randomize, but this is like the sum of all losses over the time minus the loss of the best expert. So in some sense, if there is a guy who was chosen in advance, so we don't know who is the best performer, but if we knew it, so the regret is like how far you are from knowing from the very beginning whom to follow from the very beginning. So this is the notion of regret. And then we want to minimize it. So we prove some interesting facts. So the first one is that if you don't randomize for this rule, even if I have an abstention, then I'm doomed. So there is a lower bound, which is C times T. So if I have 1,000 rounds and C is equal to 1/2, I'll have this difference at least 500. So it's awful. No learning, no online learning. Now, if you do the exponential weighting algorithm standard without abstentions, then you can have this following analog of this slow rate, like 1/√n in statistical learning. In online learning, it's square root of t log n. So it's just because we don't divide by the number of the rounds. You see, it's growing as a square root of t instead of just being linear in t, which is very important. And what we proved actually is that once I have the option to abstain, there is a randomized algorithm based on exponential weightings, such that its expected regret is at most constant. So no matter how the adversary goes, no matter what his strategy is, and no matter how many rounds there are, the difference between your cumulative like loss and the loss of the best experts will be at most constant, which is somewhat surprising if you think of it for the first time. And we have a matching lower bound, so this is essentially optimal. Yeah, that's it. Thank you.
Nikita, thank you very much. So questions? Dan, do you have questions?
So may I ask? I have
Yeah.
very stupid question. So maybe I have missed, but for the second result there was lower bound, and for the first result was there a lower bound, or it's only?
So there is a lower bound. Yeah, so we can prove like in each setup everything is tight. If roughly.
Okay. So a lower bound is more or less the same.
Yeah, in some sense, it's the same for finite sets, but we also consider maybe it like the so-called VC classes, VC dimension classes, and like it's more involved. Like you can have an infinite class, and then there are some logarithmic gaps in the bounds. But overall, this is like the precise characterization. So you cannot.
Logarithmic in what? In
There will be, if you have like a very large classes, then there will be some kind of, it will be instead of log of the size of the class, because like now the size is infinite. So you have something like dimension times the logarithm of n of the sample size.
Okay.
And from below you'll have just dimension. So there will be some kind of logarithmic gap for huge classes which are infinite, because for the sake of simplicity I only presented a finite class analysis in some sense, but we have also for some infinite classes, and yeah, so there are some logarithmic gaps in the upper and lower bounds, but for finite classes you can construct, yeah, so it's up to constant factor here.
Okay, yeah, thank you, makes sense.
And did you study what happens if you compare yourself with the minimum over the risk that you're considering?
Sorry, what do you mean, Ken?
Did you look at what happens when you, instead of comparing yourself with another risk, you compare yourself with the risk RC?
Ah, okay. So that was done by Bartlett and Weckkamp actually. So that's what I mentioned shortly. And then, as I thought, for me, it's not that interesting because they just prove 1 over square root of n convergence, which is what you expect, because it's just a loss, one of the losses, and kind of that's it. So you just have a uniform convergence result for them. So here it's very important that I get such a nice result because I know I use the special power. But the special power is it's seemingly relatively it's not super powerful, because it's just allowing me to beat a coin flips, but that's it. It's not allowing me to like output a small risk on some points. And one more thing is that if because for binary functions, if your functions f are binary valued, then of course the r and rc are the same. So formally you can say that comparing like the RC risks of 0, 1 valued functions, and by going improper, I get 1 over n. Yeah? So it will be the same risk, but my restriction is that f functions, they are not star valued in some sense.
Okay. Nikita, thank you very much.
Thank you.
So, Quentin, are you ready? Quentin? Okay. You have super cool presentation. I mean, template.
Oh, there was a sorry, I didn't mute me, but there's a question. Either intuition about what happens when we have the number of labels if there are more than 2 labels. Yeah, so in some sense, in online paper, we consider this setup, and yeah, we prove more or less the optimal result. You may check the paper. You will easily find it. But in the IID setup, it's a bit more complicated, as it usually appears.
Do you see my screen?
Yes?
In full screen, yeah?
Yes. So please, let me introduce Quentin Paris. And Quentin will talk about Barycenters and metric spaces with applications. Okay, Quentin, please.
Okay, thank you very much. Okay, so I will try to make a short presentation. I'm not so sure about the application part, given the time, but we'll see. Maybe I'll just mention some recent developments. So I'm going to talk about Barycenters and metric spaces. And in particular, I'll try to emphasize some ideas from geometry because I think they're fun. Okay, so the object I want to consider is not one of the possible generalizations of the idea of a mean value in a metric space that has no linear structure and for which you cannot define expectation of a random variable in the way you would if you were considering probability measures supported on RD, for instance. So the basic object I'm looking at is a metric space M equipped with a metric D, okay, and a probability measure on this space, a Borel probability measures that is sufficiently well behaved, so it has a second moment in the sense that for every possible B in my metric space, the integral of the square distance to B is finite. Okay, so this is what I mean by a second moment in the metric space. Okay, and so if I'm on if I'm dealing with a probability measures, a probability measure P that is satisfies this property, I define a barycenter B star of P as any minimizer of this integral when B is ranging over the metric space. Okay, so the reason why this is one of the possible generalizations of mean value is that the usual notion of expectation, okay, of or mean value of a probability P that has a square that has a second moment in a Euclidean space can be shown to be the only the unique minimizer of this variance functional. So if you replace the D squared by the Euclidean norm squared between B and X, the minimizer of this quantity would turn out to be the expectation or the mean value of your probability P. And this variational representation makes it possible to export it to the metric setting. Okay, so this is what I call a barycenter. Okay, so so from a statistical perspective, so if we want to estimate a barycenter of a probability measure, given only a sample from this probability measure, the natural analog of the sample mean, if you want, would be what we call an empirical barycenter. That would be exactly the same object as I defined before, where you replace the probability measure P by its empirical analog, okay? Okay, so these are two natural objects, I mean, two possible objects of interest in the metric space that have, so whose analysis, if you look at it in a Hilbert space, or think of H here as being RD, is very well understood. So for instance, as I already said, if you're in a Hilbert space, then what I defined, B star turns out to be just the expectation of your random variables. Bn turns out to be the sample average, and it's an easy computation to see that the expectation of the distance squared between Bn and B star turns out to be exactly the variance of your probability measure P divided by N. Okay. So the whole question that I want to address shortly is that, okay, so now if you are in a metric space for which these computations cannot be carried in such a simple fashion, so what can you say? So first, the first thing that the first question that should pop to mind is that, is it always clear that there's such a minimizer B star? Second question, if it exists, is it unique? And when it is, can you talk about the convergence of Bn towards this B star? Okay, so I want to address these three questions briefly. Okay, so about existence of barycenters. The main message is that in most reasonable scenarios, you can show that the existence is guaranteed. So for instance, in geodesic spaces, I'm going to define this later on, that are locally compact. Okay, it follows from a famous theorem called Hopf-Rhino that in this case the metric space M is proper, meaning that all bounded sets are compact. And then using classical arguments from optimization, you can show that this variance functional that you're trying to minimize is lower, so be continuous, and therefore has a minimum well, anyway. And then there's specific cases which of spaces which do not happen to be not locally compact, for which specific analysis shows existence anyway. So for instance, in the Wasserstein space that I will discuss a bit later. Okay, so and concerning now uniqueness, this is when things start to become funny and related to your geometry. It happens that this question of uniqueness is very related to geometric properties of the metric space you're considering. So roughly speaking, and I'll define curvature bounds later on, if you are dealing with a metric space that is non-positively curved, then uniqueness is guaranteed, okay? This is the case, for instance, of Hilbert spaces, hyperbolic spaces, or more generally, Riemannian manifolds that have non-positive sectional curvature, but also objects which are a bit singular, that are not smooth, like metric trees. So, okay, so these are the spaces in which things turn out to be nice. Now, for spaces with positive curvature, like a sphere, or the space of probability measures, as I will describe later on, things are not guaranteed to be unique. Okay, if so, a very simple example to convince you is that on the circle that happens to be a so one-dimensional sphere, you see that if you take the probability measure that puts weight 1/2 on the north and south pole, intuitively speaking, at least, even if the computation would have to be done, but you see that there are 2 points, B1 and B2, that are barycenter of the probability measure. So you see that on some spaces that have positive curvature, things are not always guaranteed to be unique. Okay, so in this case of the Wasserstein space, I will define it later on. Some very general conditions have been described under which we can show that the probability measure that you're considering has a unique barycenter. And this condition is that, so on the case of the Wasserstein space, the probability measure is a probability measure on the space of probability measures. Okay, and if there are elements in the support, okay, there are sufficiently many elements in the support of this probability measure P that vanish on small sets, meaning that they attribute mass 0 to sets that have a Hausdorff measure strictly smaller than the ambient dimension, then you have a unique barycenter. Okay, to put things even more simply, if you suppose that P is supported on functions that have a density with respect to the Lebesgue measure, then this would always be satisfied. Okay. Okay, so the next question we want to address is that given a probability measure, a barycenter B star for this probability measure and an empirical barycenter, can we give precise bounds on this expected distance between empirical barycenters and true barycenters? And for this, I need a little bit to define a bit of geometrical concepts. So I'm going to go pretty fast. So I'm going to consider geodesic spaces, and geodesic spaces are metric spaces for which, given any 2 points, they can be connected by a so-called geodesic. So the short definition of a geodesic is a curve that satisfies this property, okay? That for every 2 points in the interval 0, 1, the distance between gamma s and gamma t is exactly equal to t minus s, the distance between the endpoints. And this, one can show that the natural interpretation of a geodesic is that it's a length minimizing curve between the endpoints. Okay, so let me give you 2 examples of interesting geodesic spaces that will turn out to have very different geometric properties. So the first one is the space, for instance, of symmetric positive definite matrices. Sorry, I forgot the word definite. Equipped with the distance from A to B, which is the L2 norm in the space of matrices, meaning by L2 norm in the space of matrices, I mean the square root of the sum of the squares of eigenvalues of log of A minus 1/2 B A minus 1/2. Okay, so this is one can show that this provides a valid distance on the space of symmetric positive matrices. And then one can show that for any two elements in this set, AB, the curve, which is defined by this formula, okay, gamma t, provides a geodesic between A and B for this distance, D. Okay, so this is one interesting example. The second example I want to give is the Wasserstein space. So here the metric space I'm considering is the set of square integrable probability measures on RD, equipped with the so-called 2 Wasserstein metric, which is defined as the square root of the infimum over all couplings of mu and nu of the integral of the distance square between x and y. Okay, what by a coupling pi of mu and nu, I mean a probability measure on the product space, RD times RD, whose first marginal is mu and second marginal is nu. Okay, so it's known that this space is geodesic, and the geodesics can be described explicitly as follows. So if I give you mu and nu, and I take pi to be a minimal or optimal coupling between mu and nu, meaning a coupling p pi reaching the infimum in the definition of W2, and I look at the push forward of this coupling by this function, theta t, then this describes a curve, okay, in the space of probability measures that and turns out to be a geodesic between mu and nu. Okay, so I chose these two examples because they end up having two very different curvature properties. So I'm going to define curvature bounds by 0 because it's easier and shorter. So this is how you define in a very general setup in metric spaces which are not necessarily Riemannian manifolds, curvature bounds. So you say that the space has curvature bound upper bounded by 0 if for any points in your geodesic space. So I'm dealing only with geodesic spaces. If for any 2 points in your geodesic space, in every geodesic connecting these 2 points, then the distance squared from a given point P, which might be different from X and Y, behaves in such a way that the square distance from P to gamma T is smaller than this long expression. Okay, so this long expression, so probably you see that there's something that should be familiar to you. Maybe you've already done this computation in a Hilbert space. So in a Hilbert space, you would have an identity here. The square distance from P to the interpolation 1 minus Tx plus Ty in a Hilbert space would give you here an identity. And so comparing yourself with this flat geometry of Hilbert spaces, you actually define negative curvature in this way. Okay, so the interpretation is that your triangles, okay, in your space are thinner than they would be in a Hilbert space, for instance. Okay, so this is the definition of negative curvature, and the definition of positive curvature is the same thing, where you just consider the opposite comparison, meaning that your triangles are essentially fatter than they would be in a Hilbert space. Okay, so coming back to our two examples, one can show that the space of symmetric matrices with the metric I've considered is negatively curved, while the space of probability measures is positively curved. Okay, now let me just flash a few results. I don't know how much time I still have.
I think around 4 or 5 minutes. Okay,
so that's perfect. Okay, so the first result I want to mention is in the context of negative curvature.
I can done actually even more. So 7, I would say.
Okay, but anyway, I will need maybe 5 minutes. Okay, so the first example I want to give is in the context of negative curvature. So what we can show is that so for spaces, geodesic spaces with negative curvature, adding a requirement that I didn't define, that the curvature should also be lower bounded by some negative or some real number kappa. So I didn't define what it means for a curvature to be lower bounded by some kappa, but essentially it's along the same lines. then we know that P has a unique barycenter, and we can show that this inequality holds. And what's pretty surprising here is that if you look at this carefully, this is exactly, so the upper bound we obtain is exactly the term for which we get an identity in the context of Hilbert spaces, meaning variance of your probability measure divided by n. So this is pretty interesting. And also this bound does not depend on this lower bound kappa on the curvature. So from technical reasons, we had to impose this, but it seems that we might eventually get rid of this requirement. Okay, so this applies, for instance, in the context of symmetric matrices, as I said. Okay, so the other context that we looked at is the context of positively curved spaces. So so in this case, what we can show is that supposing P admits a barycenter, B star, and that we add an additional condition, which is that geodesics that start from B star in the support of P, between B star and elements of the support of P, can be extended. So this extension condition, I will illustrate it in the next slide. But basically, we're asking something a little bit more than just having a barycenter. Then under this condition, we can show that B star is unique, and that up to a constant C that depends on the probability measure P, we also have this 1 over n times the variance upper bound. So there's but this constant C is essentially hiding some information about these extendable geodesics. So I won't go into details. I'll just give you some intuition of what I mean by geodesics being possibly extended. So what I mean by this assumption is that, what has to be true is that for every point in the support of your probability P, so for every X, the geodesic from B star to X can be slightly extended on both sides in such a way that it remains a geodesic. So you see that on a circle, if I am in the situation where B star and X are opposite from each other, then you see that if I try to stretch a little bit this red line below the equator, this will not be anymore a geodesic, because then the shorter path would have to be to go the other way. So this additional assumption that I'm stating here in an informal way is saying that geodesic emanating from B star can be extended. So this condition is requiring that for every point X in the support of P, the geodesic between the barycenter B star and X can be extended in such a way that it remains a geodesic. So in the case of the sphere, this would require the support of P to be included strictly in a semicircle. Okay, strictly included. So for instance, for a probability that would have a support on the whole sphere, this would not work. Okay, so you would have to be strictly included in a in a hemisphere. Okay, so this is all I wanted to say. If you want to know more about this topic and some applications, you can look at. So, for instance, there are many things that are interestingly true in geodesic spaces. Is, for instance, Jensen's inequality in spaces with a lower curvature bound. That leads to many interesting applications. For instance, the extension of this notion of exponentially weighted average forecasting strategy in geodesic spaces. So here there's a typo. It's not non-positive curvature. It's in geodesic spaces. And then there's concerning exactly what I talked about. There are the two last papers on the list here with colleagues from the US and from Morocco, where we actually study this problem of estimation of Barycenters by empirical Barycenters. Okay, thank you very much.
Okay, Quentin, thank you very much. So, dear colleagues, do you have questions?
So I have a question. So
Yeah.
you're studying question when your barycenter is unique. Will it make sense to ask question whether there are at most finitely many of them? Because like I can like in your circle example, you have at most 2, I think. But if you go to a sphere, you can have infinitely many. So what would you imagine as a dividing line, like dimension of negative curvature part or something?
So the thing is that this, so there's a, I mean, you can, as soon as, even if you have many minimizers, okay, of this variance functional, you can talk about excess risks, which is like in the spirit of the 2 first talks, in which case you can have guarantees using empirical process techniques. But we were more interested in finding conditions that guarantee existence, guarantee uniqueness to work with. But if you, so your question is, what can you say when you have only finitely many?
No, what would you imagine as a condition for having at most finitely many?
At most,
yeah, because so you're talking about dichotomy, unique and non-unique, and I'm asking more like, would it make sense to consider trichotomy, unique, at most finitely many, or infinitely many?
Well, that's interesting. I never thought about this.
Because if there are finitely many, we can like find all of them, right? And if there are infinitely many, there is no chance we can find all of them. So from practical standpoint, this would be a nice distinction in principle.
So, okay. So if you have so I didn't define it. So if you're negatively curved, you have only one. Now, if you are, if you have an upper curvature bound by something which is not 0, it's known that your metric is locally convex. Okay, so if you have as soon as you have an upper curvature bound by an arbitrary strictly positive number, there is a radius, there is on sufficiently small sets, okay, your metric, your distance is convex along geodesics, strongly convex along geodesics with the strongly convex parameter that depends on the diameter of the sets you're looking at. So this means that locally you can only have you can only locally have one. So if you can cover your set by, so of course there would have to be a study between the diameter of the set and the size of these neighborhoods, but if you can cover your set by finitely many such neighborhoods, you can guarantee you have a finite number.
Okay, yeah, that sounds good.
So my answer is at least that for every upper bounded space, you have at most a countable number.
Okay, and if it's compact, then
you're
okay, good.
Yeah, and if
okay, so thank you. So thank you, Quentin.
No problem. Wait, I just said a mistake because on the sphere.
Yeah, on the sphere actually you have infinitely many. But yeah, okay. I was just curious. I don't have any special reason. We can discuss this sometime afterwards.
Okay, so Quentin, can you stop sharing?
Yeah.
Okay. So, Глеб, быть по-русски или по-английски?
Ну, мне сказали, что по-русски, поэтому я как дурак вчера слайды переводил с английского свои. Давайте, раз Кентан здесь, я могу слайды показывать по-русски, говорить по-английски. Вот. Если так.
Нестандартный подход. Окей.
Ну, как во Франции, так многие делают, на самом деле, ну, то есть с другой парой языков. Да. Так. Я должен уметь пошарить экраном. Okay.
Okay, so let me introduce Глеб Погудин from École Polytechnique about точная редукция динамических моделей.
Okay, yeah. So sorry, let me find a compromise by talking in English and showing the slides in Russian. I hope this will not cause much confusion, because basically
you can speak Russian if it makes you more comfortable, Gleb. I don't mind.
No, actually, as I said, I have been translating the slides yesterday, so I usually speak about these things in English, so it's perfectly fine with me. So yeah, so I will talk about exact reduction of dynamical models, and as a disclaimer, so it's not machine learning in any common sense as you would understand it. The reason I would like to talk about this topic here is basically because the problem I'm solving is, on the high level perspective, the following. So I deal with models which are sort of too big to be computed with and far too big to be reasonably interpreted. And I'll talk about algorithms that try to circumvent this. And yeah, to the best of my understanding, this is spiritually a common question in machine learning as well. So I hope that maybe some of the things I will show or discuss will help in the same sense in other contexts. And this is actually just a nice result. So, and yeah, this is a joint work with my colleagues listed below from Italy and from US. So what's this all about? So basically this slide says more or less everything about the results. So I would like to understand that some things are actually smaller than they do appear. What does this mean in the context of differential equations? Let me show you a toy example. This is purely for illustrational purposes. So assume that we have a model that models something in the real world. And this model, oh, do you see my cursor? When I point at something on the screen?
Yeah, we can see.
Okay, good. So this is the model. So this is a system of differential equations that models something. And actually the thing we are interested, assume that we are interested in the value of x1. So this is our target variable. And x2 and x3, they are here for the sake of the model, right? So they model some factors, but they are not interesting to us per se. So in this particular expression, so what you can notice is that basically the first equation has a structure, so it's actually perfect square. And in this case, we can compress this model. So this model looks like a three-dimensional model, but we can view it as two-dimensional as follows. So we take this thing inside the square, x2 plus 2x3, and we create a new variable equal to this value. And then it turns out that the derivative of this new variable can be expressed in terms of this new variable only. Okay, so this is the crucial feature. So if you just do the math, so if you differentiate x2 and x3 and combine the derivatives, what you'll get will be again double y. Why is this important? This is because now I can write the following system, which is a reduction of my original one. So I can just say that I have this new variable y and x1 together, they form a new model, which is first smaller. And second, if I restrict myself on x1, it's exactly the same. Okay, so there is no approximation going on in this case. So I get exactly the same trajectories for x1, I get exactly the same predictions and everything. But my model is, 33% smaller in a sense. Okay, so this is a toy example of the question I would like to answer. Formal statement is the following. So we are starting with the following input. We have a system of differential equations, of ODEs, which define some dynamical model. And most examples I'll talk about are from chemistry. And we have some number of variables, first L variables, which are of interest to us. And this number is usually small. So if we have 1,000 equations, we don't usually care about all the thousands of variables. And what we would like to find is to get a set of new variables which are linear in the original ones. So like in the previous slide, I have a new variable which was like x2 plus 2x3. So that these variables, they do form a closed dynamical system, dynamical model on their own. And this new dynamical model contains my variables of interest exactly, so I do not lose information about things I do care about, but this dynamical model is as small as possible. Okay, so basically I would like to make some linear transformation, which will make my model smaller, but keep the things I do care about. And there are two reasons why one may want to do this. So first reason is sort of straightforward, but it's in some sense less important. So it's if you have a smaller model, it's easy to compute. So it's easy to run simulation. And this becomes important actually if you do something like sampling-based parameter estimation in the spirit of the first talk of today. So because if you would like to estimate parameters for such ODE models, what you basically you do a lot of sampling and then simulations of the trajectories, and of course reducing the dimension may have exponential impact on the performance of such methods. And this does happen. I will mention this a little bit. But there is another very interesting feature is that after you do such reduction, it's easy to interpret, and in some sense it also may give you additional insights, because such exact reduction, they usually do not come with no reason. They usually come with there is something in the model which is not visible from the surface, but it's hidden inside. I will elaborate this when I will show you a big example. So this is exactly the problem we would like to solve, and I would like to discuss in some reasonable detail one actual example, so that to give you a feeling of how the problems look like and how the solution look like. So this is a system. The only point of the system on the left-hand side of my screen is just for you to get impressed. I do not expect you to read any sort of detail. So this is just some huge system. So what this huge system does, it models certain chemical process. I apologize if there are chemists in the audience, because I may say things that you will dislike, but that's my level of understanding chemistry. So what happens here? So there are two variables, x1 and x2, which correspond to kinase and phosphatase. These are like, small things floating around. Okay, just two types of small things floating around. And then there are 16 more variables, which are for big things with holes. Okay, so like in this picture, so there's these blue things with holes. So this system corresponds to blue things with 2 holes. And on the picture I have 3 holes, but you can consider this case as well. So there are 3 holes, and each of the holes can be in 4 states. It can be white, it can be red, or it can be white with orange thing attached, or it can be red with orange thing attached. Okay, I don't have this on the picture, but this also happens. So there are like these big blue things with 4 ports, 2 ports, and each port has 4 states. So this is how you get 16 variables, 4 times 4. And naturally, so you can consider this proteins with a larger number of states, and you'll get the absolute explosion of size of your system. Okay, so it will be like for seven ports, and this is, as far as I understand, the realistic situation. For 7 ports, you will have 16,000 equations. So it's like a huge thing. But this is roughly where it comes from. So no chemists or biologists would sit down and write this system, with pen and paper. So the systems of this size, they usually come from this sort of so-called rule-based description. So when you describe on high level that, if I have an empty port and there comes an orange thing, then it will be attached and it will be detached. So you describe several such rules, and then they can be expanded into like a gigantic ODE system. And our goal is to do something with this system. So in the setup I will talk about, I will assume that I'm interested actually in the small floating things in x1 and x2. So I would like somehow to compress the information about these big blue guys. Okay, so I would like to tame this combinatorial explosion by some sort of reduction. And what turns out is that indeed you can do this. So you can reduce this system of 18 equations to just 6. So first of all, let's just appreciate the size. So we have like half of screen, and now we have this small guy over here. But it's not the only benefit. So of course, this is a smaller system and it's much faster to compute with it. But also you see so that the variables you get, they have sort of nice combinatorial structure. So basically, they are usually referred to as macro variables. So they just say that, well, I mean, you have different chemical species here, but from the point of view of things you care about, some of them can be considered to be like the same. Like, for example, in Y2, I consider just, the total number of these blue guys with holes. And this is a very meaningful thing, right? So this is the total concentration of these blue things. That's meaningful, that's meaningful. And the other three, they are more funny. They sort of count some of them with a weight. So they're equal, but some of them should be counted twice. They correspond to some symmetric configurations in some sense. And it turns out that what the algorithm basically says, that from the point of view of this x1 and x2, these four quantities are what matters, and nothing else matters. Okay, so this is the result I'm after. So I would like to first reduce the system, and second, to see certain structure of it from this reduction, because this exact reduction usually doesn't come with no reason. So this is the prototypical question, prototypical answer. And yeah, so and if you have 7 sites, you will have 16,000 something equations, and you still get 6. So it's a very nice thing. So even if you increase number of words in these blue guys, you get the same 6 equations. I mean, get different 6 equations, but the number will be always 6. And yeah, so we have an implementation of this algorithm that does the following. So, and the state of the art before was the eRoad software, which did the following, which it was also looking for these macro variables, but what it was doing, it was just taking subsets of variables and gluing them together, saying that, like, all these things will be one chemical species for this particular case. Such question has a finite search space, but of course it's a search space with exponential size. So these people who developed this eRoad group in Italy, they are very nice and clever. They found a very powerful technique to do combinatorial search in this huge space. This sort of reduction, it doesn't give you the as much as you can get if you allow just linear combinations. So you can see that the reductions we get, this last column, may be much more concise, especially in these examples like the one I have shown before. And it's all pretty fast. So although it's Python, I know on my laptop I can compute all these things in about 2 minutes. Most of them in about 10 seconds. So it's an efficient thing. So, and I would like to talk a little bit about what's behind this, what this problem is about from the computational perspective, because so it's actually just a linear algebra problem in a nutshell. Although linear algebra of some a little bit unexpected sort. So it's a classical thing that this problem of exact reduction, it was done in the early 90s by Lee and Rabbits. It can be more or less reduced to a problem of linear algebra. And problem of linear algebra is the following. So you are given a set of vectors and set of matrices. And in this case, matrices, they do correspond to the original differential equations. They are derived from Jacobian of it. And vectors, they do correspond about the observables you would like to keep. And then basically all this reduction business is reduced to the linear algebra question about, well, I have matrices, I have vectors, and I would like to find the smallest subspace which contains my vectors and is invariant with respect to my matrices. So 2 properties, invariance and containing the vectors. And basically, like, I mean, it's not rocket science. You can solve this problem by just multiplying vectors by matrices until nothing new comes up. So you multiply vectors by matrices, you compute linear span of the things you get. If there is something new, you multiply again. And if at some stage you don't get anything new, you just stop. However, I mean, this will work, this straightforward approach. There are several subtleties. So main subtlety is that matrices are quite big. So yeah, I mean, dimensional thousands is of interest on one hand. On the other hand, they are pretty good in two senses. So first of all, the matrices are sparse. They're really sparse, very, very sparse. And somehow you know that the output of the algorithm will be always nice, because this will be some reduction, which is a structure of this model, and the model comes from nature, and nature is nice and structured. So it's almost always that the result is not horrible. It's nicely looking. And in this case, one can speed up things substantially by just first carefully eliminating unnecessarily multiplications and some standard symbolic computation tricks. So you exploit sparsity, so you don't store matrices as matrices, you do some data structures for them, and you do modular computation. So this may sound weird for people who use mostly numerical computation, but in this case, it's important to keep things exact, because every small approximation error may blow up your space and leave you without reduction. So you would like to keep things exact, and if you keep things exact, you live in rational numbers, which do grow and which may grow enormously during the computation, although the final result will be small. And in this case, what people often do, and what we have done in this case, you just do all intermediate computations modular prime, and then afterwards you can do certain reconstruction. And this eliminates this problem. So this is about how such things are solved. And I would like to mention this is the method is not really stick to the ODE systems. So you can take different equations, or I would imagine other types of models can be also tackled in this fashion. It just depends on whether there are good examples to tackle. So right now we're working with differential equations. We will be happy to work with any other sort of models if there is a feeling that they may have this sort of structure. And yeah, just somehow to finish, not all of the results you get this way are actually as interpretable as you would like to. And the question of interpretability is still a question. So because basically the reduction you find is defined up to a coordinate transformation, and if you have a nice system and you do coordinate transformation, you may get a nasty system. So out of all the possible results of reduction, one also would like to pick the one which is the simplest. So the question of how to make a change of coordinates in the system so it will become as nice as possible. And this is one of the questions. Another question is that sometimes you don't really know which things you would like to keep, and you just would like to reduce the model and then to see. And this is actually a project to bachelor students at HEC are working right now. So if you would like to talk to someone about this, you can talk to them. And yeah, there are also questions about approximation and nonlinearity. These are valid questions to extend the applicability. And I'm doing very well on time, so I will. It's nice that I'm last speaker. And the very last advertisement, I have a postdoc position open on this exact topic. So if you feel that someone may be interested in doing such things in next year, just please let this person know. That's it. Thank you very much. And I would like to thank the organizers to inviting me to, although I'm not topically exact fit. And thanks for attention.
Okay. Thank you very much, Gleb. So dear colleagues, what about questions? Quentin, do you have questions? So you turned on video.
Yeah, no, I don't have questions. Just a great talk. Thanks a lot.
Okay.
Unfortunately, I have to leave the meeting, guys. So thank you again.
Yeah, thank you. Bye-bye.
Thanks a lot. Goodbye.
Thank you.
Okay. So no questions in the chat.
Теперь, наверное, можно перейти на
русский.
Да, пожалуйста.
Или на французский.
Потому что даже в списке участников я не вижу ни одного иностранного участника.
Yeah.
Oh, there are questions and answers.
Да, спрашивают про учипы.
Я просто не вижу вопросы от участников почему-то.
Это в Q&A, это не в чате, а в Q&A.
Он не в чате, он там на отдельной.
Да, это отдельная штука. Отдельная штука. Там спрашивают, да, про учипы. Такой вопрос можно задать про учипы, безусловно. Тут ведь как бы какая ситуация. Задать вопрос можно где угодно, вопрос, будут ли интересные ответы. Вот, в случае с дифферами как бы оказалось, что есть действительно системы, которые сжимаются. С учипами я не знаю, не очевидно, я не встречал настолько огромных систем. Наверняка есть что-нибудь, что получается как дискретизация чего-нибудь. Потому что дискретизация там тоже такой взрывной рост. Но не приходилось пока поработать с этим. Но вопрос хороший. Я согласен, что это потенциально правильное место для поиска примеров.
Окей. Нет других вопросов. Я просто подумал, вопрос про УЧП изучать или нет. Такой вопрос, what about? Хорошо. Тогда, если больше нет вопросов, то спасибо всем докладчикам. Вот. Я надеюсь, что запись здесь идет. Я надеюсь, что потом ее кто-нибудь посмотрит из студентов, извлечет пользу. Все, всем спасибо.
Всем пока.
Спасибо.